Good morning, everyone. So I'm actually switching the topic completely, switching gears to optics. I hope that you do care about optics. I will try to bring across why you should care about optics in OLEDs. If you would have the perfect TADF material from chemical synthesis, there's still a lot of things that can go wrong if you build an OLED device and if you want to achieve high efficiency OLEDs. So if you are ambitious and want to chase the efficiency records of OLEDs, you should also care about optics, not just about the materials, the molecules. I would like to acknowledge people who have worked hard in this at Fluxim, for instance, Stefan Altazan, Lydia Stepanova, and Leven Penning, who are experts in optics, and another colleague at ZHAW, Christoph Kirsch. They have contributed to the optical modeling that I'm going to present. Let's see if the switching works. Maybe it's... Was there a second? Was there a second? Is it? I'm not sure. But you have two of them. Maybe I took the wrong, or it should be fine. I mean, no, wait. This one is the slot that should work. I mean.
Maybe the presentation is selected because the customizing.
Okay. Now let's. Thank you. Yes, that was the problem. Okay, thank you. So I split the presentation basically in two parts. I will start by introducing the basics of the dipole emission model, and this is related just to planar OLEDs, just planar layers. And then in the second part, I will talk about scattering enhancement tricks, which is an additional thing you can do to increase efficiency further. So in the first part, basics and tuning OLED stacks, we care about the orientation of the emitter, stringence of layers, and also refractive indices and so on. And in the scattering part, we have some examples where we look at scattering rough interfaces. This particular image is from a random etched silicon wafer. The other one is a microlens array. So you see that we can define such structures or import such structures from the experiment and use them for the simulation. Now, in terms of the software, yesterday I talked about the electrical part. Can we just get that? Otherwise it. Otherwise it may appear again. Well, I talked about drift diffusion module, and today I will talk about the emission module of the software ZFOS. Of course, you can also do optical solar cell simulation where you would use the absorption module, but then if you have light scattering structures, there's another part of the software which takes care about light scattering, which is also relevant for solar cells, not only for OLEDs. Now let's look at the motivation. A nice publication was made by Professor Kachi in 2015, where he has used a TADF called DACT2, and he achieved internal quantum efficiency 100%, and he measured 41.5% EQE, a remarkably high quantum efficiency of an OLED. And here you see just the schematic of TADF. But the actual OLED looked like this. Just put the TADF dopant into the CBP host, and then he had to first optimize the OLED stack optically. So the first thing to do is optimize layer thicknesses. You see we have TAPC and BALQ, so this is HTL, whole transport layer, and electron transport layer. And the thicknesses of these layers has a strong influence on the optical power that, or let's say here we plot the outcoupling efficiency. Optical outcoupling efficiency is strongly influenced by just the thickness of the transport layers. So HDL thickness variation and ETL thickness variation shows you nicely there's a nice optimum. You have to choose the right thickness of the transport layers in order to have best outcoupling. So that's the first step of optical modeling. Second example is that Professor Kaji also calculated the modes, the optical modes, so here as a function of wavelengths. So the green part in this graph is the outcoupled to air. You see he gets at 550 wavelengths, he gets about 30% light outcoupled, but still there is a strong amount of light, a strong part of light which is trapped in the substrate, which would be the orange part, substrate guided about 28%. So that shows that in order to get this record value, you don't get away with just the green mode coupled directly into air for a flat OLED, for planar OLED, but you have to actually exploit also the substrate guided mode, the orange part. And how can you do that? You can add a micro lens array, which is then here an image of this micro lens array. Just what works very well is a hexagonal packed dense micro lens array with hemispheres, and this film laminated on top of the OLED on the glass air interface on the outside of the OLED, and this is how he got the 41%. Well, there's another point, another aspect is the emitter orientation. If you would have just isotropic or random orientation of the emitting dipoles, you would not get up to this number. His molecules, the DACT2 TADF molecules, he managed to deposit them in a way that they are not isotropic, but slightly preferentially horizontal aligned. So in this graph here, you see that he determined the orientation of the emitter by an angular photoluminescence experiment. So exciting with blue light, measure the angular PL measure the angular PL and compare it to a simulation. The simulation here, the black line, is the simulation if assuming an isotropic emitter orientation. So that does not fit the data, but it's hard to see, but there is a thin green line which is for the assumption of preferentially horizontal orientation, and that simulation actually does fit the green measurement points. So it is a popular way to extract the emitter orientation, and so this is a nice comprehensive example where simulation was used at different parts of the project. Now, yeah.
What does letter S mean? 0.29.
Yeah, this is actually a bit of a confusion because in the literature you will find 2 or 3 different definitions of orientation. I have to, I don't remember exactly. I think this is not.
It characterizes
Yeah,
I think if I remember, it's the one that is a fraction that is parallel to the substrate and a fraction that is
yeah, it's always something like that, but
polarization is too
but in here the S equals 0 is isotropic,
Okay.
but in some other definition S isotropic can be 0.33 or 0.66 depending on how you define. Maybe Jehu, oh, you can help.
The order parameter from a literature -0.5 and -0.5 for horizontal alignment and 1 for isotropic alignment. Vertical alignment and 0 for isotropic.
Okay. This is from an ellipsometry measurement. You could also get. Okay. So I think in the set for software we use yet a different definition. I think that's why I'm a bit confused. But okay. Now let's look at the OLED lighting example. LG Chemical is a leading provider of OLED lighting panels, and if you take a commercial panel from LG Chem, you see there is a scattering foil that you can peel off, and then below you will find emission that looks a bit different than white. It's actually a bit reddish. It shows you that the pure planar OLED stack will not have a white emission spectrum. Only after you put the light scattering foil, you will end up with a white spectrum of a decent white color point. So that's one observation. And yeah, you see the slightly different color. And moreover, you see that there is, maybe not on this projection, but you see some rectangular lines. So these are the current spreading electrical lines, metal lines, that help to make a uniform potential. And this will be linked to my next presentation after lunch, which is about electrical large area simulation. So for this, so first I talk about optical simulation, and after lunch it's about electrical large area modeling. Now also the same commercial panel also shows that in terms of viewing angle, a lot is happening. If you measure with an angular setup, we have an option for our Pius instrument to measure the angular spectra. That's what we have done here. So if you peel off the scatter film, you get an intensity of light that increases with viewing angle. Sorry, I cut off the scale, but it's here at angle 0. You don't have 0. You have a finite brightness, but it increases significantly. And if you laminate the scatter foil, you can increase by a factor of 2 roughly. So it's very strong enhancement thanks to the light scatter film. And moreover, the angular dependence is strongly dependent on the angle. There is a certain viewing angle where you have a lot of emission, between 40 and I hardly can read the 40 and 60 viewing angle degrees. Okay, so this commercial successful example shows that you have to care about angular dependence, about scattering film, and it would be nice to have reliable models that can describe this. So what about reliable models? So there are, in terms of multi-scale, multi-physics modeling, in terms of the optics, this is the right-hand side. We can think about thin film optics. The dipole is embedded in a very thin OLED layer, but then we have a thick substrate and then the external foil, so there is light propagation more in a geometrical optics fashion. So we have a transition from thin film optics to ray optics. So the software tools also should adapt to these both worlds that are combined in the same OLED panel. And in between, we might have some microstructure optics, which could be wave-like or ray-like. Now, let's start with thin film optics, so the dipole emission. How can it be described? So we have excited molecule where this, which can be described as a classical dipole that oscillates. If this positive-negative charged dipole oscillates, then there will be emission of the electromagnetic wave perpendicular to the orientation of the dipole. This is just a sketch, but it nicely shows that you have an antenna effect, kind of the emission, the wave goes away in a perpendicular direction to the dipole. That's why it is beneficial. If you have a planar OLED, you should place the molecules horizontally, and then the emission is nicely going perpendicular away from the OLED. Then that's the first observation here in the sketch in terms of orientation, and then in terms of power that is emitted, we have to realize that we have an excitation, so we have a periodic excitation, and we have a damped harmonic oscillator. And the damping is actually, the reason for damping is that the electromagnetic wave gets reflected from the metal that is nearby, and the reflected electric field shows up here in the right-hand side of the equation, and it means that the luminescence dynamics that the time constant of decay is actually altered because of this reflected field at the electrode. So the dynamics, the excited state dynamics, will be different in an infinite medium rather than here in the device where you have thin film layers and layer interfaces and metals nearby which reflect the wave and damp the oscillation. That's why the luminescence lifetime that you measure in a device really depends on the distance of the emissive layer to the electrodes. Okay, some basic formulas. If as a chemist you measure the PL quantum yield, where's the PL quantum yield on this slide? I think it's this Q0 would represent the PL quantum yield, and B0 would be the power emitted by the dipole if it's in an infinite medium. Then the non-radiative part is simply 1 minus Q0. So we always have a term here which accounts for the non-radiative decay. But the light comes out with Q0 times B0. And then the influence of the cavity can be plugged in to this quantity F. But that's where the computation happens. The model tries to calculate this factor F. It's the Purcell factor, which influences the amount of light, the light power that is emitted. But it's only affecting the first term, not the second term. So if the PL quantum yield is not 100%, you always, with tuning the OLED stack, you only modify the first term. The second one is always the same. And then you could either calculate the power, or you could also look at the dipole lifetime, which goes with the inverse of the power. Yeah, dipole lifetime can be measured with decay experiments. And then the F quantity here is actually a numerical integration of another term, F of U. And U is something like an angle of emission inside the emissive layer. Namely, it's the wave vector k, the in-plane component of the wave vector, divided and normalized by the wave number, which is somehow related to the sinus of the theta E. Theta E is the emission wavelength. Yeah, but let's accelerate a bit. The OLED is a thin film device. We have emission from the organic layers. And here we have a sketch of two cases, a planar case and a hypothetical macro lens that you would add on. And you see the big difference is if you put a macro lens, the light can go straight through. Well, there is a refractive index is a bit higher here than in the glass, but nevertheless, you could say that it goes straight through, and the light hits the glass air interface in a normal angle. That means there is no refraction. But if the rays hit the glass air interface at an oblique angle, then you can, if the angle is between 0 and 42 degrees, then the ray will go straight through. But if the angle is larger than 42 degrees, then we have total internal reflection. That's simple ray optics. And that means that the light is bouncing back to the device and is being trapped inside the device, and we call this glass mode. And then there is another critical angle. If we have a refractive index change from the glass to this organic, from 1.5 to 1.8, then we also have another critical angle above which we have guided modes. So we really only get the fraction of light in the first cone here, and this is typically 20% for a simple planar OLED. And you see here the substrate guided mode can be 25%. And last but not least, we can also excite some charge fluctuations, some plasmons in the metal, which can be a big portion, a big loss as well. And to quantify this, we can do the simulation. For one particular OLED, we would have, let's say, one ETL thickness, one thickness of the transport layer, And we should choose it such that we have the highest IOC, is outcoupled light into air. So the air mode is the red area here. And you see that the blue part here is the substrate guided modes, which air mode and substrate guided mode can account for up to 50% of light that, so that usually the idea is to not only collect the air mode, but also exploit the mode in the glass. And then significant losses, as you can see, are happening with evanescent coupling part, which then this evanescently coupled part increases if the emitter layer is too close to the metal, meaning if the ETL thickness is too thin, that we have a lot of losses. So you should make ETL thick enough that that this coupling reduces. Okay, so I've already presented here one typical simulation result, but you have to decide first, what do you want to simulate? Do you want to simulate outcoupling modes? You can imagine that if you want to know the total amount of light or total fraction of light going into air, you need to actually integrate the emission angle from 0 to 90 degrees to kind of a hemisphere integral in all polar angles. So this computation takes a bit longer than if you would just be interested in this emission spectrum at 0 degrees. So you have to choose in the software, do you just want the spectrum at a certain angle? Then you choose a spectral mode. And then the previous example was mode analysis, where this integration over all viewing angles is carried out by the software. We call it mode analysis. And the other option in between is to actually resolve this term here. We had a term, an integrand here, f of u, and you can actually plot that quantity below the integral to further study the physics. So that's the third option, and I will show you some example of this dissipation power analysis. But the first example is just looking at spectra in 0 degree viewing angle up to 60 degrees. What you see here is not solvatochrometry, but is simply just a blue shift that always will be there as a function of viewing angle. And in the color diagram also, the color point can move a bit with viewing angle. This is just normalized intensity. If you would look at the unnormalized intensity, you would have, usually you want to have most emission in vertical direction and kind of a cosine behavior, how it drops. At least for display application, this is what you want, but for lighting, it's a bit different. We did, a long time ago, we did some validation experiments of the model where we fabricated a PLED which has emission through semi-transparent electrodes. So we have bottom and top emission. Bottom means the light comes out through the glass. And for two thicknesses of the active layer, we measured the symbols here are the measurements. Bottom is red curve. So the thin device, 80 nanometers, we could call this is kind of a tuned OLED, because then we have most light emission in forward direction at 0 degree. But if you increase the thickness of the OLED, then typically you don't have the maximum light out at 0 degree, but at some other angle. So this is the typical signature of a detuned OLED, which is too thick compared to the wavelengths of emission. But the good news here is whatever you have, the simulation can nicely reproduce the measurement. And for the OLED display industry, it's also important to deal with color filters. If LG Display would use a white OLED with 3 components in the spectrum, they would still add a color filter. So the simulation software should cope with this. Now the problem is that the OLED stack is a thin film stack, but the color filter is very thick. It's 0.3 micron, and you might have a glass in between even. So we need to have an arbitrary situation of thin and thick films. and our software can do that. You see that from the white spectrum with the no color filter or thin color filter, we have the red curve, which is a white OLED. And for thick color filter, we can suppress the red part and the green part, the blue and the red contribution. We end up only with the middle peak being the green output. So that's, behaves as it should. And another example of thickness variation is the layer here, ETL and HTL, and the emission is, the emissive dipoles are placed here near the interface. You see that, again, similar to the Professor Kachi paper on TADF, also here we have an optimum combination of HDL and ETL to give most light output. And you see, because we have this interference effect, the emission color will also strongly depend on the combination of thicknesses. So even if the molecule itself would emit a nice green, if you make a bad device, this same OLED material looks like orange color point. Okay, now I'll have some other examples on, it's a bit more understanding what's going on with the emissive modes. So this middle option here, if you want to calculate this f of u integrand in the integration for the Purcell factor, you can visualize the dissipated power versus this in-plane wave vector, or versus effective refractive index, or u in-plane. And this is how it typically looks like. In this representation, the small effective refractive indices, this is related to the sine theta, where theta is the emission angle of light in the emissive layer. So the light outcoupled to air would be the first region here. Second region would be anything between refractive index 1 and 1.5, which corresponds to the glass substrate. This would be the trapped amount of light in glass. And then there are typically some sharp modes which happen between effective refractive index 1.5 and 2. So these are the boundaries for the refractive index of organics. We see some sharp peaks, and last but not least, we also have plasmon coupling that shows up for even larger n effective values. So this is the details of dissipation power, and for mode analysis, the software just integrates in these 4 regimes, integrates to get the fraction in each mode. And here's to visualize what can go wrong if you have your emissive molecules too close to the metal back electrode. So this OLED, we want to extract the light in a top direction here through the glass substrate. If your emitter relative position is too close to the metal, you have a strong evanescent coupling part here. If you move it further away from the metal, then this is more suppressed. Guided modes are a bit enhanced, but the overall outcoupling will be also better than on the left case. And as I said, the software will, you have to integrate these different regions, defining the mode, and then you get the total picture, how much is coupled to air, how much is absorption loss here in green in this case, and guided mode yellow. And in this example, we have a lot of evanescent coupling. More than 50% of power is evanescently coupled. It really depends on the OLED structure. Now, in terms of emitter orientation, there are a lot of publications out that have studied emitter orientation and have shown that you get higher efficiency for more horizontal emission. This is an example of IRMDQ ACAC. Is a molecule that in this host tends to orient horizontally. And we have here emitter orientation randomly, you would only get 25% outcoupled to air. But if you have 100% horizontal emission, here quantified with alpha, you would get 35% of light into air. So that's the ideal case, and the realistic case would be 80% preferential horizontal orientation, and you get 28% outcoupling into air. Yeah, but these numbers will really be sensitive to the choice of layer thicknesses. Here's a variation of the whole transport layer thicknesses. You see that for a given orientation, for instance, the realistic 80%, you have a strong modulation of the achievable light outcoupling efficiency. Now, that was this ERPI phosphorescent molecule. How about TADF emitters? The Adachi group has published 2014 a nice publication where they have actually made sure that the emitter is oriented in a decent way. What they have done, they actually varied the deposition temperature. If you increase the temperature in the substrate during evaporation, what happens is you can destroy the horizontal orientation, this preferential. You get, for the red curve, you see at high temperature, you get PZ represents the vertical dipoles. You get more of the vertical dipoles rather than at low temperature where you have less vertical dipoles. So the deposition temperature can influence the orientation of the molecules as it is forming a film. And how do you actually measure this curve? The angular PL is measured in a way that you have the organic film on a glass substrate. You attach a big hemisphere outcoupling lens, and then you excite with a short wavelength laser, and the emission is detected versus the angle, viewing angle. And you may wonder why do we always have this funny dip here, very sharp dip in this kind of data. It's interesting to realize that this is nothing to do with interference. It's more like a simple optical effect that it always happens at a typical angle, and the reason is probably that there is total internal reflection for light, that for the first part of the measurement we have emission downward and also upward because this kind of emits in all directions. But for small angles from 0 to 40 degrees, the light is lost upwards. But for larger angles above 40 degrees, you have total internal reflection because of the refractive index step between organic and air. And this will fold back. It will reflect PL light, which otherwise would be in air, and it will add up to the measured quantity in the down direction. That's why we always have kind of this sharp dip. But the overall curve will be very sensitive to the orientation of the emitter. Now, this is a very popular method to determine the orientation, measure it, and fit it with a model. Another alternative would be to just look at the angular electroluminescence, which was pointed out by Flemmich and colleagues. So if you would measure the angular electroluminescence spectra of the OLED, you can also then fit it to the model and get a characteristic shape here. And we have here an example. I think this was ERPI ACAC emitter. We had these measurement data points here in the symbols. For an isotropic assumption, the angular electroluminescence signal would be the black curve. And for a 100% horizontal orientation of emitter, you would expect this funny red curve with a completely different shape. And the reality in the experiment is in between. So we see it's closer to isotropic than to parallel. In fact, the quantity here was 74% parallel, which is in nice agreement with the literature value of 77%. So that's an alternative way of determining the emitter orientation. And there's even a third option to look at the luminescence decay constant tau versus layer thickness, which is also a sensitive quantity for emitter orientation. But now let's look at the optical property of layers. We have a lot of molecules, or like to be non-isotropically deposited. So in order to have an accurate model, it's worth to implement birefringence. So far I talked about these red molecules that emit the light, but if they are only doped into a matrix, then there are still a lot of matrix molecules in orange here, which also have some orientation. And they could be preferentially horizontal. So there could be a birefringence, an anisotropy in the refractive index of the host material, which should be included in the model as well. And with that, then the fit of a green simulation here, the green line with the measurement, can be even somewhat improved further. Now let's, so birefringence is a topic that affects not only the emissive layer, but birefringence can also be exploited for layers outside of the emission layer, so transport layers. And this is an example we have here, motivated by this publication from the Nates group, where they have studied the birefringence of HDL layer and ETL layer. And in our software, you see here, you enter, for the simple layers, you just add one number, but for birefringent layers, you add an ordinary and an extraordinary quantity for the refractive index. And we do that for each HDL and ETL. And what we calculate is the outcoupled mode. So the scale here is 0 to 1 variation. So red would be a lot of outcoupling efficiency. That's 74% outcoupling. It's a huge number, which you can achieve if both the ETL is birefringent as well as the HDL is birefringent. So the extraordinary component here of the refractive index, if that one is low for ETL and for HDL, then we can achieve a very high optical outcoupling efficiency. But be careful, what is simulated here is outcoupling from the OLED into the glass and not yet into air. So you will still lose some part. So this is not realistic unless you add a big macro extractor glass or some other micro lens array. But it shows a huge difference. So instead of having OLEDs with isotropic transport layers, not birefringent, you would go from 54% outcoupling to 74%. So you can gain a lot. But the main reason here is not the birefringence itself, but rather the fact that the wave sees a low refractive index. And the low refractive index is also exploited here in this recent publication from Professor So's group. And they have nicely demonstrated that there is an electron transport material here which has a useful property, that it has a relatively low refractive index, 1.65, compared to 1.7 or 8 of typical organics. And this already helps to increase light outcoupling. So instead of measuring external quantum efficiency above 10% for the reference device with two other HDL layers, if he uses the low index, this is ETL. If he uses the low index ETL, the external quantum efficiency is higher than 20%. So it's a remarkable increase of quantum efficiency by just selecting a refractive index. Well, you need to find a material that works with low refractive index and still has good charge transport property. And what he understood from simulations is that the reference OLED with the normal ETLs, he would only get 22% light outcoupled. But if the low index ETL is used, he gets 33% air mode. And this can be understood by looking at the dissipation power spectrum. Here in this calculation, he varied the refractive index of the ETL. And you see what happens is that if the refractive index is 2.0, for instance, a high refractive index, then the emitted power is nicely coupled into the plasmon mode. So power is lost. Everything in the fourth region here is lost to the metal. But if the refractive index of the ETL is smaller, then this plasmon peak moves to shorter in-plane wave numbers. And then we have more, the red curve here is for the low index, we have more outcoupled power. So by this calculation you can actually rationalize why we have enhancement of outcoupling. Another thing to worry is emission zone fitting. I already mentioned it briefly yesterday. Where does the photon come from? You can also do some sanity check, assuming a certain emission intensity in blue here, or the distribution, and see whether the algorithm could reproduce that. But now let's go to the second part, which is light scattering. So far I've only talked about OLEDs which have planar interfaces, planar layers, planar glass air interface. But now we introduce light scattering, and for that we need to also include large scales and layers that are incoherent, and we want to bridge the gap. So bridging the gap means we need a model that can deal with the OLED stack with its very thin layers, and then maybe there is a planarization layer in between, and there's a substrate. Both of these are thick. Then there could be an interface, a glass that could be structured in a certain way, either wave optically structured or macro optically textured with a macro lens array. So this is the general situation. And now the design challenge is, this scattering be like? Should it be very broad in terms of angle? So if you hit the interface at a certain angle, there will always be some refraction, so the direction changes if the refractive index top and bottom is different at this layer interface. But then there is a spreading, a scattering lobe here. How strong should this be? Good outcoupling, that's the design question. And at the end, you should also think about the OLED stack. What do you need for the OLED stack? Should it be very reflective, or should it, should it be very transparent? Both things can be problematic. If the OLED is not reflective enough, then the scattering properties are not exploited well. And so there's a compromise between both here. So one example here is if we assume Lambertian scattering with a certain strength, and with the strength of scattering we can quantify with the haze. Haze is defined as how much light is scattered for an incident light intensity. So 100% haze means every light is scattered in other angles. 0 means all the light is going in the straight line through the interface. So the reference case, we have outcoupling with a number 20 here, and for strong scattering we have a monotonic increase. Oh, that's a first example where the scattering interface was placed inside OLED, meaning that on the inside of the glass where we deposit the OLED, we put a planarization layer, a high index planarization layer, and the glass has 1.5 refractive index. So you not only need a structure, but you also need a refractive index contrast between glass and the high index layer here. For this, the same example, we can calculate the spectrum. If you have 0 haze, so no scattering, you would have this, the bottom line here in the spectrum. But if you increase the scattering, the outcoupled spectrum changes its shape. So that means that color point will also be affected, as we have seen for the LG Chem example, where the scatter foil does influence the color that you get at the end. Another example here is for a thin film flexible OLED, where the OLED was deposited by the host center on a flexible metal foil, and then thin film encapsulation layers have been used. And the challenge here is these thin film layers are kind of thick, so optically you have some layers that are propagating incoherently. And then at the end, we here optionally add a scatter foil. And the scatter foil can indeed help to direct light out into the air rather than leaving the light trapped in the OLED. This is now a comparison of measurement and simulation. On the left, we see luminance versus angle for the planar OLED without the scatter foil. And you see for the blue case here, where we add a strong scatter foil, we have a strongly enhanced outcoupling, and more nicely also the luminance is less dependent on the angle of viewing. And the intermediate case is a foil with a moderate haze, a moderate scattering property. The graph on the right is the color point. You also see that with the scatter foils, the color point changes. But if you look at the lines and the points, the simulation quite well reproduces the measurements. So you can use simulation to tune the properties. So you can, in the model, you could change the particle concentration, for instance. The particle concentration of this scatter film, so it is contained of a matrix and scatter particles. The amount of particles will influence the scattering property, and you see there's a maximum here. The two experimental foils have these two numbers here. And so it's well understood. It can be really used to optimize the outcoupling. And I mentioned before that the OLED stack itself, there is some issues about the stack. There is reflectivity is important. And from this simulation here, you see that if you optimize the flat OLED, you would have a certain ETL thickness that is optimal. But then if you add the scatter foil, the optimum ETL thickness will change. So there is a compromise between the two. You cannot optimize just the OLED stack itself and then just buy a foil, whatever it is. You should optimize them both together to get the desired optimum light outcoupling. And an important concept to describe scattering is the BSDF, is a way to describe the scattering behavior. What it means is it's the bidirectional scattering function. If it describes how light of a certain incoming angle to the interface, how this light is being spread into outgoing angles. So for instance, at 25 degrees incoming angle, light is being spread over several angles of outgoing direction. And more interestingly, in this case, this is a glass, just a rough glass. The rough glass will even allow for transmission above the angle for total internal reflection. So this amount of transmitted light is important because it helps to escape the light from the glass substrate. This kind of quantity is a nice thing to describe a scattering interface. And here's a study where we actually assumed that this rough glass this interface is outside to the air, and the OLED stack is in the other side. And this BSDF quantity describes this interface here for transmission, and the second matrix here, BSDF, is for reflection. You always need the transmission and reflection property of the interface. And now this is one option, and we want to compare this to another scenario where we put the scattering interface inside. So there's a planarization layer, and then the planar OLED on top. And now you notice that the BSDF data slightly looks different. In fact, this BSDF, we have a wider green cloud. It means more scattering than over here. Why is that? Here we have an index contrast between glass and air. And here we only have an index contrast between high N and 1.5 for glass. So this is less strong scattering than outside. So it's try to quantify the overall performance. So we compared both cases. We have the flat reference case without any scatter interface, and IEL is the internal scattering interface, and the EEL is the external scattering interface. You see that in this case, surprisingly, the external rough interface performs better than the internal scattering. And you could even combine both, have a dual side rough glass, and it gives you even more enhanced outcoupling of light. So this is a quantitative prediction of amount of light you get out. Okay, this is now in the spectral mode where we just look at the outcoupled light, and you may ask how much fraction, what's the overall fraction of mode of light that you get out. And for this, we adapted also the calculation of modes analysis here. If you would have an OLED with just a planar OLED here, the example shown here, then you would again have air contribution, light going into air, just 21%, substrate guided 32%. But now if you add the microlens array on top on the glass air interface, then we have the situation on the right. Now we are able to harvest the light that would otherwise be trapped in the glass, and we get up to 38% light outcoupling. But we do suffer for some more absorption. So compared to the left case, there is some absorption because the ITO and the metal electrode in the back, they do absorb some light. If you have more rays scattering back and forth, you also have more absorption in the OLED. So that's another thing to keep in mind. But it shows that we can not only quantify the outcoupled fraction for the planar OLED, but also for OLED with some scattering structure. Okay, so the typical simulation workflow is that you need to define the scattering structure. Is it a topography, so a texture? Is it a film with particles? Or is it a micro nanostructure? And then we internally calculate the BSDF quantity. And this BSDF describes a certain interface, but of course you could add another scattering interface. And at the end, we get the angular or the fraction of light in different modes. Okay. Yeah, this is last slide. Okay. So if there are remaining minutes, I can again make a demo of the software if you don't mind. So I tried to show you that modeling of OLEDs, state-of-the-art, record OLEDs, optical modeling is important to get the best out of your high potential materials. And our software can calculate the enhancement potential. And I've shown you several examples of low index, dipole orientation, birefringence. And if